So let's do this question here from May, June 2013, paper 1-3. So this is about roots of polynomials. So what we have here is that the roots of the equation are this. Roots of the equation, this little thingy are alpha, beta, gamma, and delta. So it's your quartic equation. And the sum is denoted by Sn. The sum of the roots with the nth power for each. And using the relation x square or otherwise, show that alpha, beta, and alpha square, beta square, and gamma square, and delta square roots of the equation. So because the roots themselves are being squared, the substitution is going to be squared here. And then we have this little thing which I have to show. So this is how I do it. So if y equals to x square, then x equals to root y, as we know. So what we have here is, I'm going to write down root y to the power 4 minus 4 root y whole square plus 3 root y minus 2 equal to 0. So we have here y square minus 4y plus 3 root y minus 2 equal to 0. Now I'm going to take this one to the other side because I want all of them to have even powers. All of them to have positive integer powers. So, and also I want this to be quartic as well. So we have here 2 minus 3 root y. Now we can just do squaring both sides. So we get, I'll do a bit of a motivation because I feel like this is not going to work that way. So I'm just going to, instead of sending this little guy to the other side, I'm going to send it like this. Y square minus 4y minus 2 whole square equals to 9y square. So as a result, 9y. So as a result, we have and it equals to 4y square. So y to the power 4 minus 8y cube minus 4y square. Oh wait, 4y square and 16y square. So we have here plus 12y square. 16 minus 9 is 7 plus 4 equal to 0. There we go. So next it says state the value of S2 and hence show that this little guy. So what I'm doing here is eh, so the sum of these roots is supposed to be Sn. So the sum of this one is supposed to be alpha square, beta square, gamma square, and delta square. Which means if I directly put S1 here, then I'm supposed to get, this little guy right here directly. S1 of this equation. So S1 of this equation is supposed to be minus b by a. So this is supposed to be my answer of S2 of 1. So this means that I need to show S8. Okay, I see. I also need to, okay, it says to prove S8 equals to 8S6. So on like that. So if I go back to the first, to this equation, y to the power 4 minus 8y cube plus 12y square plus 7y plus 4 equal to 0. So the way we denote this is like this. So I need to find out S8, which basically means S4 of this equation right here. So what is it S4? So if I use that notation again, if I use my roots alpha square, beta square, gamma square, delta square, then So from here, what I do is that start off with S8, I mean on this equation, which means I have to just multiply the entire thing by things like you would expect. So what I'm going to do is, okay, what I'm going to do is that if I have S1 of this little thingy, it's exactly the same as S2, right? So if I have S4 of this thing, then it is exactly the same as S of 1, which means that if I have S4 of this equation, as I know from here, S2 is going to be exactly the same as that thing there. So it means that if I write down here S1 and S2, S3, S4, I just multiply that by 2 so that I can get S2 there. So I can just write S8 because it's going to be alpha square, beta square, gamma square, delta square. So I will end up getting a larger degree equation like this: y to the power 8 minus 8y to the power 6 plus 12y to the power 4 plus 7y square plus 4 equal to 0. Now there's nothing here because there's nothing there. So S8 minus 8 S6 plus 12 S4 plus 7 S2 plus 16 equal to 0. All right. We do not multiply the constants out with the number of roots here because we have a variable here. If it's a complete constant, then we do so. So what we do know is 7s2 is S2 is 8. So we have here S8 equals to 8 S6 minus 12 S4 minus 52 minus 16. So we have here 8 S6 minus 12 S4 minus 72. I was first of all thinking about trying to, mix things up with S4 and whatnot, but I just realized that I needed to show this thing here. Yeah, right. So there we go.